All right, let's take a look at factoring this expression here. Now you'll see this is a degree 3 polynomial when we expand it all out. I want to be able to factor this. You can see here the x minus 2 happening here and here. As a starting point for ourselves here, we can use the method of substitution just to clean this up a bit. I'm going to let t equal x minus 2, and we get the following here. Now I want to be able to factor this degree 3 polynomial. When you're going through your factoring techniques, you should take a look at, like, do we have difference of squares, some or difference of cubes? Both answers are no for that. There's no GCF. On this, I don't see factor by grouping working as well. We have an odd number of terms. So at this point, we want to try synthetic division. Synthetic division is typically your last resort in breaking that polynomial down. If you notice here, I've got the 4 and the 7. That has a difference of minus 3, so it's almost working. I'm going to try, let's try synthetic division at minus 1. And factoring this using synthetic division, I get the following decomposition. Taking a look here, this is a degree 2 polynomial. I can go ahead and do charting, try to break this down. So let's go ahead and factor this using charting. Doing so, we get the following. And you'll see by going ahead and doing charting here, I end up getting the following decomposition. Now this wasn't a t, this was an x minus 2. So let's go ahead and sub in an x minus 2 for our t values, giving us the following. So going ahead and doing that, letting t equal x minus 2, we get the following. Expanding and simplifying, we have the following decomposition. And you'll see here that this expression is equal to x minus 3 times 2x minus 7 times 2x minus 3. Let's take a look at another example here. This time we're given a degree 2 polynomial. This is a quadratic. You can see the power of this is going to be a 2. But the idea here is that you're seeing, in this case we see a 1 minus p and a 1 minus p. This lends itself to substitution. What we're going to do here is I'm going to let t equal 1 minus p, just so we can get a better look at what this quadratic looks like, in which case it's 5t squared plus 20t plus 15. Now, if you were asked to factor this alone, ignoring the fact that we have the 1 minus p, just focusing our attention on this quadratic here, you're going to first always look for GCF. Always look for GCF, in which case we factor out a 5, and I'd be left with t squared plus 4t plus 3. And then you have a simple trinomial here to factor, which factors into t plus 3 times t plus 1. But like we talked about before, that is not just a t, it's actually a 1 minus p. So subbing that in here, we get 1 minus p plus 3 times 1 minus p plus 1. Rearranging this, we get 5 times, this end up being negative p plus 4 times negative p plus 2. Typically, you want your variable to have a 1 in front, not a minus 1. So I'm going to factor a minus 1 out of this expression and this expression. Both of those minus 1s will multiply together to just give you 1. So therefore, this ends up being 5 times p minus 4 times p minus 2. So it turns out that this expression right here is equivalent to, in factored form, 5 times p minus 4, p minus 2. All right, in the following example here, they give us a degree 3 polynomial, and they want us to show that this polynomial has at least one irrational root. And the key word here is irrational. If we examine the end behaviors of this polynomial, we can quickly see that it has to have a real root. To see this, notice the following. You'll notice here as x approaches positive infinity, I can see my polynomial p at x approaches positive infinity. And likewise, if x approaches negative infinity, we can see our polynomial approaches negative infinity. So visually, we have the following. If you take a look at our Cartesian plane here, I've got a polynomial tending towards positive infinity as x gets large, and then a polynomial tending towards negative infinity as x gets very small. But we know that polynomials are continuous. So I know that in this case here, these polynomials are connected. Again, I don't know the exact structure of the function, but I know it has to look something like this. I've got a y-intercept that's positive, so I try to make it there. But what we do know, because of this, we know that it must cross the x-axis. If it crosses the x-axis, we know that it has a real root. So what we need to show now is that, in fact, it is a real root, but more precisely, that root is irrational. This is where the rational root test comes into play. If you missed the lesson on the rational root test, I will link that in the top right-hand corner. For those of you who've seen it, let's apply the rational root test. So using the rational root test, I know that if my polynomial has a rational root, because the leading coefficient here is 1, it's just going to be factors of the constant term. So therefore, I'm going to look at plus or minus 1 or plus or minus 7. So if my polynomial does have a rational root, it must be one of these 4. So let's go ahead and do synthetic division on these 4 and see if we can get a remainder of 0. And you can see here, I tried synthetic division at 1. I did not get a remainder of 0. I tried at minus 1. I did not get a remainder of 0. Tried at 7, did not get a remainder of 0. And I tried it at minus 7. I actually didn't even finish calculating. I could see it wasn't going to come out to be 0, so I didn't do it. Didn't continue it. So in this example here, you can see I've gone through all 4 possible rational roots. None of them worked. So therefore, this real root, which we know exists, is not rational. It therefore must be irrational. So this is an example of, by using your end behaviors, you know that the polynomial has a real root. Applying this further using your rational root test, we can see here if none of them work, that root that this polynomial has must be irrational. Now, it could be the case the polynomial has more irrational roots. That's something we have to talk about later. But in terms of this example here, showing that it has at least one irrational root, just applying your end behaviors and your rational root test will do the trick. All right, we're going to take a look at the idea of factoring incomplete squares. So the idea with an incomplete square is you have a situation where you can see this is a perfect square, right? The square root of x to the power of 4 is x squared, square root of 9 is 3. It would be great if this was true, because if I were to expand out my first term, I would get an x to the power of 4. If I square the last term, you get 9. But when I expand this out here, I get first times second times 2. What will be generated inside of here was 6x squared. So if I expand this out, like I was saying, you're going to get x to the power of 4 plus 6x squared plus 9. We don't have that. We have a 2. So these are not equal, right? We do not have equality yet. But with an incomplete square, what you can do is you can tack on and add or subtract what you need to do such that it comes out to be true. So what we have here is I have this 6x squared, but I want a 2x squared. So I'm going to subtract off a 4x squared. And you'll see now that we've done that, what we have here is I have x squared plus 3 all to the power of 2 minus 2x all to the power of 2. We can then treat this as a difference of squares, right, where this takes the place of my x and this takes the place of my y, to which we get x squared plus 3 minus 2x times x squared plus 3 plus 2x. And just rearrange this a bit, we get the following. And you can see here when I expand this out and rearrange this, we get 2 quadratics taking the product of them. Both of these have a discriminant, which is less than 0, and therefore these have complex roots. So this is now fully factored in terms of the real number system, and this is an example of factoring using incomplete squares. Let's take a look at another example of this. And the next example here, same idea. This is a perfect square, and this is a perfect square, and again, it would be ideal if we had the following equality. This was equal to x squared plus 3, quantity squared. But again, when I expand this out, you're going to end up generating a 6x squared plus 9. I do not want a 6x squared. I want a minus 19x squared. So in this case here, again, this is not equal currently. But what I want to do is I want this to come out to be a minus 19x squared. So therefore, we must subtract off a 25x squared. And you can see here 6x squared minus 25x squared is in fact minus 19x squared. And by doing so, we end up getting x squared plus 3 squared minus 5x to the power of 2. And your difference of squares formula kicks in again, giving us the following. And you can see here, applying the difference of squares formula, we end up getting the product 2 quadratics yet again. A quick discriminant check on these will yield a discriminant equal to 13. So it does have real roots, except for they are irrational. We'll have to use the quadratic equation to find these. Let's go ahead and find the roots using the quadratic equation. Doing so, we get the following. So we end up getting the following 4 roots here. One root is x equals negative 5 plus or minus root 13 over 2. And the other 2 roots are x equals 5 plus or minus root 13 over 2. Writing this out in fully factored form, we have the following. And you can see here we have x minus our first root, x minus our second root, our third root, and our fourth root. And now this is fully factored. Thank you.